All right, hello everyone and welcome. So today what I'm going to show you is using Google Sheets instead of Excel. So the other video was on Excel. This video is on Google Sheets. And I'm going to show you essentially exactly what I showed you on Excel except on Google Sheets. So what I'm going to show you is how to graph data with Sheets. I'm going to show you how to make a best fit line, to create an equation of that best fit line using Sheets and finding slopes. I'm also going to show you how to find Rsquared values and what those Rsquared values mean, as well as how to establish relationships between two sets of data. And then lastly, we're going to be looking specifically at looking at the relationship between area. So area, I got a whole column here of area, and how the area of a circle depends on diameter. So what I have here is two different sets of data. One of them is diameter. This is the independent variable. It goes from 1 meter to 10 meters. I can see that because diameter in parentheses is measured in meters. And area is measured in meters squared. And these are the corresponding areas of a circle with, so this is the area of a circle with diameter of 1. This is the area of a circle with diameter of 2, area of a circle with the diameter of 3, etc., etc. So it goes all the way down. I got this from a website called Math is Fun. If you want to know specifically what that website was, I go back to the Excel tutorial. But what we're going to do now is we're going to use this data that we got to try and see if we can find a relationship between that data. And again, in science, what we're looking for is a linear relationship. We're looking for a straight line relationship between these two things, and we can use Sheets to help us try and see how good that data fits that relationship. So what I'm going to do is I'm going to graph this data. What I recommend is doing the independent variable on the left. So I got diameter, which is the independent variable on the left. And depending on the diameter, that gives you the area. So the dependent variable is on the right. That's the easiest way I find to graph with Sheets and Excel, honestly. So what I'm going to do now is I'm going to highlight all of the data right there. So I'm going to highlight everything. And then I'm going to go over to this icon over here that says Insert Chart. And I'm going to select Insert Chart. And it gives me, it starts off with a bar graph, which may be good for some data. A lot of businesses use bar graphs. I'm pretty sure I've seen a lot of biology data using bar graphs. But in physics, we tend to use scatter plots. We want to use scatter plots because that helps us. It's just better for physics. Anyway, so if you see over here, you get this whole little. So here's where your chart is. Here's where your chart is. Oh, and you want to make sure that you have a title. So we have a title here that says area versus diameter. It's even got the units in there. That's a good title. I might just add, just to make it a little more specific, so we'll say of a circle. So this is not just area versus diameter, this is area versus diameter of a circle. And then we got along Y is the area, and the units are correct. Those are meters squared. That's the units I want to use. And then on the horizontal axis, we got diameter, which is in meters. That is what I want to use. However, the chart is not what I want. I want a scatter plot, so I'm going to go over here to the chart editor, and you got two columns here. You got either data or you've got customize. What I want to go right now to is data, because I want to change my chart type, where it says column chart. I don't want a column chart. I want a scatter plot chart. So I can go through all of these here, and I want, there it is, scatter. So this is what you want, scatter. You don't want this with the big spheres. You don't want the bubble chart. You want a scatter chart. So I'm going to select scatter chart, and there we go. That's exactly what I want. And if you see, all these data points correspond to data in my sheets over here. So if I select here, I got 6. That's a diameter of 6 and has an area of 28.3. And if I look over here, 6 has an area of 28.3. But that's not all I want to do. So now I've finally got the scatter plot going on here. I now want to create a best fit line of this scatter plot. And you could just look at it right now, and you might notice like there's a bit of a curve, and it almost looks like a quadratic. So we're probably not, we're going to get a best fit line. It might not be the best fit line though. But right now we got this curved looking shape, and we'll see how good that data fits the best fit line. So to do that, I'm going to go back to the chart editor here. I'm going to go back to the chart editor, go to customize. So select customize. And then there's all sorts of things you can go through. I can actually, what's nice about Sheets is I can click. If you notice, I click the vertical axes right now, and I can change it to anything I want. I can click the horizontal axis, and I can change this to anything I want. So I can directly click on the chart, or I can go over to the chart editor and select things like chart style. I can change the style, or I can click chart axes and titles, and I can change things like the chart title, the horizontal axes, and the vertical axes. But again, the first time I graphed this chart, it was wonderful the way it was, except for a little bit of detail that I added at the end. So I'm happy with that. But what I want to create is this best fit line. So to create the best fit line, I'm going to go to Series. So I want to go to Series. I'm going to select Series. And if you notice from the Series section here, I've got all sorts of different things that I can do with it, but what I want to select is trend line. Trend line is the phrase both Excel and Sheets uses for the term for a best fit line. So trend line is showing the best fit line. So I'm going to select that. It asks me for aesthetics things, basically like line color, line how dark I want my line thickness, all sorts of things like that. It also gives me line type. It should select linear as the default, but in case it doesn't, in case it selects these other ones, you are looking for a linear relationship. Again, in science, we are looking for linear relationships. The other thing I want to change here is it says label. It says none. I don't want to label it none because I am interested in the equation. I'm interested in the equation of this best fit line. So in order to show the equation of this best fit line, I'm going to select label. So even though it says none, I'm going to change that none to use equation. And if you notice right here on the graph itself, it gives me the equation of the line. It's 8.638 times x plus negative 17.267. So that's the equation of my line. It's a linear relationship that it's showing, that this line is showing. It's a straight line. Of course it should be a linear line. But now I want to see how good my data fits that line. And to do that, I'm going to select what's called, it says show R-squared. So these are called, this is an R-squared value. So I'm going to select that box over there on the right, and it gives me an R-squared value of 0.95. Which, if I'm to be honest, with real data, 0.95 is a very good R-squared value. Because R-squared is a value between 0 and 1 that tells you how good your data is fitting this best fit line, this trend line. The closer these data points are to this trend line, the closer R-squared gets to the value of 1. The further away this data gets from the trend line, or the more scattered and just absolutely all over the place that this data is, the closer the R-squared value gets to 0. So R-squared is the number between 0 and 1 that tells you how well your data points fit this trend line. And again, if this was real like data that I had collected, 0.95 wouldn't be bad. But I would still look to see if I can manipulate it to get a better R-squared value. And that's what I'm going to do here. I'm going to say, okay, 0.95, Not bad. That's pretty good. So this could be the equation that's fitting my data that shows me the relationship between area and diameter, but perhaps I can do better. So what I'm going to do now is I'm going to just sort of put this aside and see if I can do any better. And how I do better is I'm going to rearrange the data in some way to see if I can get a better relationship between these two values. Area versus diameter might not be good, but perhaps area versus diameter squared, or area versus diameter cubed, or area versus 1 over diameter, or I can do all sorts of things. And what's nice about sheets is I can easily and quickly try and check to see if these relationships are better than others. So what I'm going to do right now, though, is I'm going to select all the area data. I'm just going to copy it and paste it over here. So I just copied all the area data and directly pasted it right over to column E over here. So there's nothing too fancy about that. But now I want to instead, what I'm going to do instead of diameter, I'm going to see, well, how does diameter squared change that relationship? Does it make it more of a linear relationship? And if so, that shows me more that the area depends on diameter squared, diameter squared, and the units would be then meters squared, because meters times meters is meters squared. How good does the area depend on diameter squared as opposed to the area depending on diameter? So if I get a more linear relationship between these two things, I can say that these are the values that variables that depend on each other more than, say, these two variables. All right. So what I'm going to do now, I'm going to show you something that's going to blow your mind. That's going to help you through all your classes, throughout all your upper division high school classes, science classes, maybe even math classes, who knows, as well as when you go beyond graduating Cypress High School and into university. You will be thanking me, and I will graciously accept your thanks. So, okay. So what I'm going to do now is I want to square all these diameter values. So you could go through a calculator and go 1 squared, 2 squared, 3 squared, 4, and you may have some of these memorized too. So the operations definitely get a little more difficult. But just to show you how useful this thing is, I'm going to just perform the operation of diameter squared for just this value right here. So the first diameter I have here is 1 meter. And I want to square that 1 meter. So in Sheets, I go to this cell right here that I have highlighted. I'm going to select equals. And I hit equals, and I've got A, column A, row 2. So that's column A, row 2. So I'm going to hit equals, and I got the equals there, A, 2. And then I'm going to use the power symbol, squared. And then I'm going to hit enter. And notice it says 1. That's because 1 squared is 1. But now I'm going to select that cell again. If you notice, I got my mouse arrow right now. You can see the mouse arrow right there. But if I go to the lower right corner of that box, it quickly becomes a plus sign. It becomes a black plus sign. So it goes from a mouse arrow to a black plus sign. So if I got that black plus sign, I actually can select and drag that plus sign all the way to the data point of 10 meters of diameter. And then I'm going to let go. And sure enough, if you see, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, yada, 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 it goes all the way down. So it just did that operation for me, just repeated the operation until it made it all the way down to 10 squared, which is 100. And you can see this if I select the data points. So if I see d squared, it gives me, if you see up over here, it says A2, which is the column A, row 2, squared. But if I go down it actually goes to, so for D3, it shows me the operation being done here is A3, it's A3 squared. And if I go down to D4, it's A4 squared. D5 is A5 squared, etc., etc. So it's just performing, just by doing that simple trick, it performed the operation multiple times in repetition. All right, so now that I got this data here, now I want to graph these two against each other to see whether or not they form a linear relationship. So once again, I'm going to highlight this. Once again, I'm going to go to charts. So the insert chart icon over here, I'm going to click it. And once again, unfortunately, it gives me a bar chart. So I make sure that under chart editor, I'm under data. I go to chart type. And now I'm going to go to scatter. I select scatter, and that's looking like much more of a linear relationship right there. Just to double check here, let's see, we got title is area versus diameter squared. That's good, that's what I want, but I'll make it a little more specific. So for a circle, boom, there we go. And I just click directly on it. Again, you can do all sorts of different ways to do this. My vertical axis looks good though, and my horizontal axis looks good. So now I want to create my trend line. And if you recall, how I create a trend line is I go to chart editor here. I don't want data, I want customize. So I go to customize, and I can go down to series, select series. I'm going to select trend line. It says linear, that's good. If you're looking for any aesthetic things, you can go to these other options here. But I also want to make sure that my label, that I'm using my equation. So this is the equation that I have here of this best fit line. And lastly, to make sure that equation is properly fitting the data, I'm going to select show Rsquared value over here to the right. And hopefully, if you remember, what do you want that Rsquared value to be close to? Hopefully you remember, it's 1. And sure enough, if you can see here, I've got an Rsquared value equal to 1. Typically with realistic data, you don't get an Rsquared value equal to 1. In fact, if it did equal 1, I'd be a little suspicious. But I grabbed these things off the off of a math website on the internet, so of course the data is going to be really, really good. But if you notice, though, I got a my equation here. My linear equation says that the equation is it's y equals 0.785x plus 0.011. Those of you who may be catching on right about now are probably thinking like, well, wait a minute, I know that the relationship between area and radius is pi, right? Area equals pi r squared. That's something you learn in geometry. But this slope here is not giving me pi, it's giving me 0.785. What gives? So I'm just going to select that right now. I'm going to put in this cell 0.785 and say, that's strange. What's up with that? Why is it 0.785? And in this case now we got to look into the equation to see what's going on here, what gives. And I want to point out really quickly before I go in any more detail that I've got area versus diameter, not area versus radius. This is area versus diameter. So hopefully that puts a little, wait a minute, in your head. But I'm going to look at this right now. So I got the equation here, area equals pi r squared. So if I graphed area versus radius squared, I should get a slope of pi. But of course, what I have here instead in my data is area versus diameter. So if I did, so what I want to figure out is how does the diameter depend on the radius? So you could probably think of, right, how does the diameter depend on the radius? Well, the diameter is just half of the radius. So the radius is d over 2. It's the diameter over 2 right there. And then I could then plug this in. I could plug in that d over 2 into r. So if I did that, I would get area equals pi d over 2 squared. And then you can simplify that. You can simplify that because the square distributes, right? It goes to the d and it goes to the 2. So that would be simplified to, so I'll say or I'll just put an arrow. There we go. Put an arrow. Another way to write that is a equals pi d squared over 4, right? Because you got the, again, the squared goes to the d and the 2. So d squared, and then you got 2 squared, which is 4. All right. And you can simplify that even further. I can bring this 4 over to the pi part over there. And so another way to write this, I'll write or in this case, is area equals pi over 4 d squared. All right. So looking at this now, so finally, okay, I got this thing simplified to where I want it now. If I graphed area versus d squared, my area would be the vertical part of my graph. This would be the y part of my graph. And then the horizontal part of my graph would be this entire d squared value. So this would be like the x part of my graph. So if I was to create a graph of area versus d squared, and you get some data points, blah, 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 that looks a little more realistic than the data points that I had, and you created a best fit line off of that, the slope of this line, so let's see, if I just made a rise over run, the slope of this line, this would be the change in area, and this would be the change in d squared. So that'd be the change in d squared. And so the slope would be the change in area over the change in d squared. Okay, so that would be the slope. And again, in physics, we are constantly looking at slopes and areas under curves. That's a big thing we're looking for in physics. So I could rearrange this whole equation here. I could rearrange the whole equation by, I'm going to divide both of these sides by d squared. I'm going to divide both of these sides by d squared. Because that'll essentially give me what the slope looks like. That's the area over d squared. So I'm going to do that, and if I divided both sides by d squared, I would get the d squared on the right cancels out. I get area over d squared, and the slope of that then would be pi over 4. So hopefully you can see that then the slope that I would get would be pi over 4. Because that'd be the area, the change in area over the change in d squared. Change in area over change in d squared would be pi over 4. You can plug in pi over 4 into your calculator or any other way you feel like doing it and get a value for that. But I could also go back over here. So my slope, if you recall, my slope of this graph is 0.785. 0.785. And then the number I got here from my slope is pi, 3.14, yada, 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 divided by 4. Let's see what happens if I, what's nice is you can do that directly in Sheets. So I'll just click a random cell here, and I'm going to select equals, and I'm going to do the operation pi over 4. So you could write 3.14, yada, 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 or you could just write pi. Careful though, Sheets wants you to do capital P, capital I. That's the number pi right there. It gives you this open parentheses. Long story short, just close the parentheses, and if I hit enter, it gives me the number pi. So there's the number pi. Hopefully you all agree with that. So I can select that once again, and but I don't want pi. I want pi over 4. So I'm going to do pi divided by 4, and then I'm going to hit enter again. And if you notice, it gives me the number 0.85. Oh gosh, I keep saying 8. Sorry. 0.785. And it gives me numbers beyond that. But if you notice, 0.785, that's exactly what I have over here as my slope. So I can see that the relationship between the area and the diameter is not pi. That's the relationship between area and radius. The relationship between area and diameter is pi over 4, or 0.785. And so you can, I've shown this graphically as well as analytically. So hopefully that helps you with your spaghetti lab. Good luck and have fun. All right. Bye-bye. Thanks.